Indicate which of the following are exact numbers. All right. This is important when we deal with significant figures because significant figures only counts when it's a measurement, not when it's counted. So the mass of a piece of paper that would have significant figures, right? We're measuring it. We're putting it on a scale. So this is not an exact number, right? It's a measured value. The volume of a coffee cup, again, it's measured, right? It's length times width times height, right, to get the volume of the coffee cup. Number of inches in a mile is definitional, right? So it's counted. So it's an exact value. The number of ounces in a pound, again, that's definitional, right? It's defined as how many ounces are in a pound, so that's an exact number. So you wouldn't look at sig figs with that. That's not a sig fig situation. We only worry about significant figures when we measure. Number of microseconds in a week. I don't know. This is a weird one. You know, they consider, right? It's a measurement how fast the Earth is going around the sun, how fast it spins. So this really, I have a problem with this one. This one isn't actually definitional, it's measured. So kind of skip that one. This is easy. Number of pages in this book, right? It's a measured, it's an exact value. You're not measuring it. It's the definition of the book. How many pages in the book? What is the number of significant figures in each of the following measured quantities, right? So again, this is where we deal with sig figs, right? You were able to get to the nearest kilogram with 1, so that's a 3 sig fig measurement. With B, you were able to measure out to the hundredth of a second, but you weren't measuring anything to a thousandth of a second, but you weren't actually measuring anything until you got to the hundredths of a second spot. So there's only 2 sig figs in this measurement. Whereas with C, you're telling your reader you could have gone out to the 10,000th of a centimeter. So that's a 5 sig fig measurement. Again, you're not measuring anything in D until you get to the hundredths position, right? So there's only 3 sig figs in that measurement. And when you're looking at E, you're saying you could get out all the way out, right? You're estimating out at the 10,000th position. So again, 5 sig figs. Now this one's weird, right? F you wanted to put a decimal point in. I don't know what it is without the decimal point. If they put the decimal point to the nearest gram. You put the decimal point in a 0, then it's to the nearest tenth of a gram. If I wanted this to the nearest 10 grams, right, if that's how crummy my scale is, right as a 2 sig fig number, I'd have to put this in scientific notation. Round each of the following numbers to 4 significant figures and express the result in standard exponential notation. All right, exponential notation is only important when it's important, right? I mean, if you can write a number without it, that's better, right? We only use exponential notation when we need to. So I'm looking at A. The last reportable digit would be the 5 followed by the 3, so I would just drop the 3. All right, and I'd have 4 sig figs in this number. Looking at B now, if I want a 4 sig fig number, looking at the last reportable digit being the 9. So I've got to round that up to a 10, right? So then I'd have to write this in scientific notation in order to only have it be 4 sig figs. So move the decimal point, multiply it by 10 to the 5, right? So I have a 4 sig fig number. Don't have to do with that with C. If I'm looking at the last reportable digit being the 3 followed by a 2, I just drop the 2 off. I put in exponential form, but it wasn't necessary. A lot of zeros with D, right? So it's 0.00025788. 8 is the last reportable digit there, followed by a 7, so you round it up to a 9. Last reportable digit is the 2 followed by a 0, so you just drop that 0 off, right? Put it in an exponential form. Again, we only use exponential form when it's necessary. It was necessary in B. Had to do it. That's the only way you can write that number in 4 sig figs. Carry out the following operations and express the answers with the appropriate number of sig figs. All right, so when we're adding, we look to degree of accuracy, right? My measurement 2.65 is to the nearest hundredth. So that's my least accurate measurement, right? So my answer would have to be represented to the hundredth. So the last reportable digit there is that second zero, right? Rounding rules, if it's, they're just showing here, right? Pulled this out of the book. Just showing here again, you're looking at the least degree of accuracy, which is the 10th position in this one. So drop off anything that's not to the 10th position. So my answer would be 17.00. Same with subtraction. My least accurate measurement was to the 10th, so that I can only represent my answer to the 10th. So I'd round to a 10th. Different with multiplication. If I've got a 3 sig fig number multiplied by a 4 sig fig number, I just look at which had the lowest number of sig figs. So my answer would have to be in 3 sig figs. I went back to an earlier problem, or one I gave on the worksheet. If I want to figure out the volume of this, right, it's length times width times height, a 2 sig fig measurement times a 3 sig fig measurement times a 3 sig fig measurement, I'd have to put my answer in the lowest number of sig figs. So with multiplication, it's easy. Just look for which number had the lower number of sig figs, and you round to that. They want the density, right? So a 2 sig fig volume divided into a 5 sig fig mass. My answer can only be in 2 sig figs. So back to this one, right? So 3 sig figs divided into multiplied by 4 sig figs, your answer would have to be in 3 sig figs. Division. If a 3 sig fig number is divided into a 3 sig fig number, my answer would have to be rounded to 3 sig figs. So that's how easy it is. Looking at unit conversions, a bumblebee flies the ground speed of 15.2 meters per second. Calculate its speed in kilometers per hour. So the first thing we do with these unit conversion problems is we write down what we were given. All right, so I want to convert meters per second to kilometers per hour. So I just focus on converting one of them first, and then I go to the other one. So again, when you're converting, right, you write down what's given, and then you find some conversion factor that's going to get you out of the unit that was given to get to another unit, right, a desired unit. Just noticing here, right, if I'm doing fraction by mass of oxygen and magnesium oxide, the total mass of magnesium oxide is 40.03 grams. Out of that 40.03 grams, 16 of those grams are oxygen. If I wanted to know the fraction, right, grams divided by gram, I end up with a unitless value, right? That's what a fraction is. Fractions don't have units. So again, unit conversion. If you divide grams into grams, grams cancel. So if I divide seconds into seconds, seconds is going to cancel, and I'll now have this in meters per minute. If I multiply by the conversion factor to go from minutes to hours, minutes divided into minutes will cancel minutes, and I'll have it in hours. So that's what I wanted. I wanted hours in the denominator. Now I want to look at converting from meters to kilometers. My conversion factor is for every 1,000 meters, I have 1 kilometer. And if I multiply across, all the units cancel except for the ones I wanted, which was kilometers and hours. So the way you punch this in your calculator is you multiply by the numerators, 15.2 times 60 times 60, divided by the denominators, divided by 1, divided by 1, divided by 1. Well, that's a non-function there. Divided by 1,000 gets me to the relationship between how many kilometers I would be moving per 1 hour. All right, lung capacity of a blue whale is 5 times 5,000 liters. All right, convert this to gallons. Well, I don't know. I'd have to find a conversion factor that gets me from liters to gallons. So where would I find that? Oh, I know. Google. Right? I just look up, right, unit converter. I want to go from gallons to liters. So for every 1 gallon, it's 3.7851 liters. So there's my conversion factor. I want to put liters in the denominator, gallons up in the numerator, so I can convert. A lot of gallons. Actually, I guess less gallons than it was liters, right? I think I skipped C. Yeah, we didn't do the how tall the Statue of Liberty was. I went to the bamboo one. You're given bamboo. Amazing, right? One day it's going to grow 60 centimeters. Crazy thing. Convert this growth to inches per hour. So again, you write down what's given, centimeters per day, and I want to get to inches per hour. So I look for a conversion factor to get me out of centimeters, or I look for a conversion factor that's going to get me out of days. All right, so every 2.54 centimeters, that's 1 inch. Now I've got inches up in the numerator, and days to hours. Oh, the conversion factor is for every 1 day, I got 24 hours. So notice I put days up in the numerator because I want to cancel days down the denominator with my 60 centimeters per day. When I multiply across now, I'm left with what I want, inches per hour. So 60 times 1 divided by 2.54 divided by 24 gives me how fast this bamboo is growing in inches per hour. Wow, that's crazy. You can watch the bamboo grow. What is the density of cyclohexane when a 25.0 cubic centimeter volume has a mass of 19.45 grams? So density is mass over volume. So we take grams divided by the volume. I got a 4 sig fig number being divided by a 3 sig fig number, so my density is in 3 sig figs. Experiment requires 15 grams of cyclohexane. When a 25 milliliter volume has a mass of 19.45 grams, what's the volume that should be used? All right, so we're going back, right? If we had our density, right, we figured it out. We now have a 15 gram sample. So this is what it is. Write down what's given, right? You're given 15 grams of cyclohexane, and they gave you a way to find the density. So we did that in the last problem. We figured out what the density is. For every 1 cubic centimeter, I have 0.778 grams of cyclohexane. So they want to go convert from grams to volume. So that's what density is. It's a conversion unit, right? For every 1 cubic centimeter, you have this many grams of cyclohexane. The question is, how do I use this to go to cubic centimeters? Well, I want to get out of grams, so I put grams in the denominator to cancel grams, and there it is. I've gotten to cubic centimeters, right, what the volume is. So multiply across, 15 times 1 divided by 0.778 grams, and we've converted to cubic centimeters or milliliters. 3 sig figs divided into 3 sig figs gives me a 3 sig fig answer.